Have you ever wondered what's the difference between an ABC sequence and an ACB sequence? I'm not talking about symmetrical components, the positive sequence or the negative sequence. I'm talking about the phase rotation. Does it have any practical implications? In practice, does it really matter whether your source or distribution is ABC or ACB? Do you know which one of these two is most prominent? Are there real-life examples of certain geographic regions, states, where you have both ABC as well as the ACB sequence? When we're talking about line-to-line voltage, VAB, do you know whether VAB belongs to ABC sequence or ACB sequence, or both? In this video, I'm going to go over all of these questions in detail. It is an extract from a live training session that I had conducted in my FE Electrical and Computer Exam Preparation Program and the PE Power Exam Preparation Program. I'm confident that after going through this discussion, you will have a better appreciation of ABC versus ACB in the context of three-phase system. Two more things that you should understand about three-phase circuits are the sequences, ABC and ACB sequence. Now, unless mentioned otherwise, you can safely assume ABC sequence. Interestingly, majority of the cases that you're going to encounter throughout North America, throughout US, Canada, by default, you are dealing with ABC positive sequence. But there are certain exceptions where ACB sequence exists, such as in Texas, such as in parts of California, such as in parts of Japan, for example. So that's where you have to be careful, both theoretically and practically, and make sure that in practice as well, when you're specifying equipment, when you're actually doing the installation and commissioning, you verify the phase sequence. So what is the phase sequence? That's the question. Phase sequence ABC, which in the context of sequence components or symmetrical components is also known as a positive sequence, although there is fine distinction between the two. ABC basically means that your phase A voltage is going to peak first, followed by B, followed by C. So if you literally hook up alligator clamps, okay, oscilloscope on the three phases, this is basically what you're going to see. All right. In terms of phasor representation, with a counterclockwise rotation, which is always assumed, from a positive x-axis standpoint, okay, reference is our positive x-axis. You will have phase A first. Now imagine me giving it a 120-degree twist. So after A, what am I going to see? B. Now B is sitting over here. B is being followed by C. Another 120 degrees, I end up with C. ABC, ABC, ABC. Clear? All right. So phase A as a reference, 0 degrees. Phase B, lagging behind by 120 degrees. And phase C, either leading A by 120, you can look at it like this, or lagging B by 120 degrees. Now, there are some practical implications for this, such as VAB, VBC, and VCA will only exist in the ABC sequence. Okay, very important concept to understand. So when I'm saying VAB, it's basically VA minus VB, correct? So that's the delta between these two, VAB. And when I'm taking the delta between phase B and phase C, which arrives first? Phase B. So this becomes VBC. This becomes VCA. Clear? In a positive sequence, this is the key. You will never have VBA. You will never have VCB. You will never have VAC. I'm not sure if you previously had ever paid attention to this or encountered it, but this is fine detail which requires thorough understanding in order to properly appreciate it. So when you compare and contrast it with our ACB sequence, remember I told you that this cannot exist in positive sequence, VBA, VCB, and VAC. Check this out. What do we have over here? We have VAC. We have VCB. We have VBA. These are all good. In the negative sequence, VCA cannot exist. In the negative sequence, VBC cannot exist. In the negative sequence, VAB cannot exist. Can you see this? Okay. The contrast between the two. So there are practical implications to all of this. This is not all just wishy-washy, abstract, hypothetical. All right. So when we are dealing with the ACB sequence, we have phase A being followed by phase C being followed by phase B. And this exists in Texas, in parts of California, in parts of Canada, but these systems are actually minority. Majority of the systems, more than 90% are ABC sequence. Okay. The idea is that phase A leads C leads B. Okay. So 0 reference, minus 120 for phase C instead of phase B because we are dealing with ACB. And then we have VB, right? Y network. When we are dealing with a Y network, there's some very obvious things that stand out. Even if you have very elementary, basic, fundamental, rudimentary understanding of AC systems, if I have a single phase source connected like this, pumping current out onto a line, okay, another source connected like this, pumping current out to a line, another source like this, we can clearly see that the current that is being pumped by this single phase generator or single phase source, let's call that current as phase current, is equal to the current that is ending up on the line. Clear? It's very obvious right in your face type of illustration. Same is true for B, same is true for C. And this is one of the very important observations and features of a Y network, that the phase current of a Y network is equal to the line current of a Y network. Okay. Actually, this particular observation is the basis of square root 330 degrees. I find that students who struggle with square root 3 and 30 degrees never take 10, 15, 20 minutes, 30 minutes, maximum an hour to properly understand the Y network from the circuit setup to its key features and compare it with delta network. And same is true for delta when compared to Y. All you need to do is to take 15 to 30 minutes very carefully and calmly working through these steps. And you don't need to memorize square root 3 and 30 degrees once you have this understanding once. Okay? So the line current on a Y network is equal to the phase current because of this very reason. Okay? Now, what ends up happening is that if the line current and phase current are equal, then basically there's going to be something off on the voltage side. Okay. So what I help my students go through this in the program is that we calculate the line to line voltage. And it's pretty simple. I'll quickly do this with you right now over here. We have VAB. Okay. So this is my phase voltage with respect to neutral. It's only a 5-minute derivation. So please pay attention for next 5 minutes. And I promise that you will have a better appreciation of where the square root 3 and 30 degrees are coming in from in the Y network. okay? Or at least a much, much better understanding of where square root 3 and 30 degrees are coming from in the y network, okay? And it can save you from a lot of trouble down the road. So I have my phase voltage with respect to neutral, small a, small n. Whenever we have small letters, they emphasize what? Source side, okay? So this is my phase A voltage. It is 0 degrees. We are dealing with the ABC network. Unless mentioned otherwise, the network is always ABC, okay? In an ABC network, we have B following A or lagging behind A. So if A is 0 degrees, B must be minus 120 degrees. We are not doing BC, but if you were to do BC and VBC, I strongly recommend that you do that, right? Then we can list C as well. C is going to be minus 240 or minus 240 plus 360 because you can add or subtract 360. This is how it ends up being 120, okay? So VAB is basically the delta between phase A voltage and phase B voltage. Clear? Since this is a balanced system, the magnitudes of both A and B are equal. 0 degrees for my phase A, minus 120 degrees for my phase B. So this is equal to V phase minus 120 degrees. All right. Okay. So what are we going to do from this point onwards? It's pretty simple. We are going to do the polar to rectangular conversion, and then we can bring it back into the polar domain. So this is r cosine theta plus jr sine theta. So let's work this out. If I have V phase 0 degrees, this becomes V phase cosine of 0 plus j times V phase sine of 0. Correct? Cosine of 0 is a 1. So this becomes V phase plus j times sine of 0 is actually a 0, 0. So this is V phase. Okay. Notice that this guy is simply a V phase. Let us take care of V phase minus 120. So V phase minus 120 degrees is equal to V phase cosine of minus 120 degrees plus j V phase sine of minus 120 degrees. Correct? Any issues? When you punch in cosine minus 120 degrees, you are going to end up with a minus half. When you punch in sine minus 120 degrees, you're going to end up with minus square root 3 by 2. Okay? Make sense? So V phase is being multiplied with both of them. There's a j over here, and that's how you end up with this. Now what I'm going to do is I'll simply collect the real terms together, and I'll keep the imaginary term on the side. This will result in 3 by 2 V phase plus j times square root 3 by 2 V phase. Now, if I were to go back into the polar domain by first extracting square root 3 and V phase, because remember, in 3 by 2 V phase, I can actually write this as square root 3 dot square root 3 by 2 V phase. So there is actually a square root 3 hiding in here, which I pulled out, and that left me with 1 square root 3 by 2. Okay. And then obviously over here, we have clearly a square root 3 that is hiding over here. When I pull that out, I'm left with a half. And then obviously the j over here and the V phase are pulled out from both the real and the imaginary components. So what I basically have is square root 3 V phase angle of this. So how did I make a jump from here to here? It's pretty simple. So if I have a phase angle of theta with a magnitude of, let's say, 1, it becomes cosine theta plus j sine theta, correct? And if I have this as 30 degrees, this is cosine 30 degrees plus j sine 30 degrees, which is equal to square root 3 by 2 plus j half. And that's exactly what I had in this bracket. So this is basically, if you want to further break it up, it's square root 3 v phase multiplied by 1 times phase angle of 30 degrees. Okay. Now let's take a step back. We are too deep into math at the moment. We need to keep track of the big picture. What were we doing all of this calculation for? What was on the left-hand side of the equation from the very beginning? Our good old VAB, correct? So if I carry VAB on the left-hand side, look at what I've ended up with. It is telling me that my VAB is equal to square root 3 times V phase with a phase angle of 30 degrees. This guy here. Okay, so let's unpack this. Which phase does V phase belong to? The first phase. Okay, this is important because we are saying that there is a 30-degree angle. Okay, all right, make sense? So if I write this as VAB is equal to square root 3 multiplied by the magnitude of phase A with an angle of 30 degrees on top of the phase angle of phase A. This is actually what is going on. That my line-to-line voltage is equal to square root 3 times the magnitude of phase A voltage, or the phase that appears first in the line-to-line voltage, with an angle that is 30 degrees larger than the angle of that phase. Okay, so when I'm referencing VBC, let us write VBC over here. VBC is a line-to-line voltage. It will be square root 3 times larger in terms of magnitude than the phase B magnitude. Why did I pick phase B? Because that's the first phase that is appearing over here, with a phase angle that will be 30 degrees larger than the phase angle of phase B. So which means that VBC will actually have a phase angle VBC will be equal to phase angle of VB, which is minus 120 plus 30 degrees. This is a level of understanding. Once you develop it, you will have no issues dealing with square root 3, 30 degrees. Okay? That's how we go about dealing with the Y network. And this derivation really does not take long. I tell my students to go through the same exercise for VBC, tell my students to go through the same exercise for VCA, I tell the students to go through the same exercise using the ACB sequence, and you will always end up with this. And this is a key observation. And if you want to learn more about preparation of FE Electrical and Computer exam and the P-Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.